Thanks everyone for coming. Let me welcome you all to the Kwangil lecture on mathematics in our time. This is the sixth in a series of lectures honoring our late colleague Gil Ko. The goal of the Ko lectures is to communicate the importance and beauty of mathematics and its impact on science, technology, and society. Before I introduce our speaker, Ingrid Daubechies, I'd like to say a few words about Gil Ko. You can see more details about Gil's life on the back of your program, so I'll start with Gil's arrival at NC State in 1964, when he joined the mathematics department just after receiving his PhD. During his long career at NC State, he authored over 70 research publications, published a book, and served as mentor for 11 PhD students. Gil's lifelong commitment to education was a cardinal feature of his tenure at NC State, and he taught and influenced thousands of students over the course of his career until his retirement in 2004. He continued to teach part-time and actively participate in the research and educational activities of the department until his death in 2009. His generous spirit, powerful intellect, and profound integrity remain an inspiration to his friends, family, and colleagues. We'd like to especially thank the Ko family, who is here, who have provided generous support to start this lecture series. Our speaker today is Ingrid Daubechies, the James B. Duke Professor of Mathematics and Professor of Electrical and Computer Engineering at Duke University. Professor Daubechies earned her PhD in theoretical physics from the Free University of Brussels. In addition to seminal advances in time-frequency analysis, she is best known for her breakthroughs in wavelet research and contributions to digital signal processing. Some of the wavelet bases and other computational techniques she developed were incorporated in the JPEG 2000 standard for image compression. Professor Daubechies has an impressive list of achievements. I'm just going to give you a few out of a very, very long list. She received the National Academy of Sciences Award in Mathematics in 2000. She served as president of the International Mathematical Union from 2010 to 2014. She received the Nemers Prize in Mathematics in 2014. She was just awarded the Simons Foundation Math Plus X Prize for her research in signal processing and applications to biology. Have you heard some of that in the colloquium talk yesterday? She's also very likely the first and only mathematician to have been granted the title of Baroness by Belgium's King Albert II. And today, Baroness Daubechies will tell us about mathematicians helping art historians and art conservators. Please join me in welcoming Ingrid Daubechies.
Thank you. It's a pleasure to be here, and I hope you will enjoy this lecture. So, mathematicians helping art historians and art conservators. Some of you may have recognized that these are the hands in the picture of Michelangelo on the ceiling of the Sistine Chapel, where one hand is the Lord and the other is Adam's hand. And I'd like to think that we do it in both directions. On the one hand, art historians have actually given us very nice problems that in some cases became research problems for my student. On the other hand, we are also helping. So I'm going to talk about some of my own work in the second half of this presentation, and in particular it's work in collaboration with the North Carolina Museum of Art, where there's an exhibit going on that I recommend warmly to you and about which I will talk a little bit. And that will be work together with my students and postdocs and collaborators, with people from NCMA and also with an artist in the Netherlands. But first I'm going to give you two examples of work by other people who did very mathematical work and that helped art conservation and art history. The first is Massimo Fornazier, who is now a professor in Munich. And while he was still a graduate student, he did some work for which he then later received a very big prize from the International Society for Industrial and Applied Mathematics on the fresco reconstructions, reconstructed frescoes by Mantegna. So it starts at the end of the World War. By mistake, a church was bombed, and there were priceless frescoes by Mantegna and others that were destroyed. Here is a reconstruction of the chapel in which you had these frescoes. In fact, ironically, 2 bottom frescoes were preserved because they were not present in that chapel at that time. They had been removed because they had some water damage, and they were in a museum being conserved, and that's why they were preserved. But the other rest of it was all reduced to rubble of this size, and these little pieces of rubble, because these were priceless frescoes, had been collected in big crates. And every so often, when conservators in the museum in Rome, where they were preserved, where they were kept, felt that they had some time on their hands, they would open it and try to piece some things together and realize how hopeless a task it was. So, in start of the 90s, they said, well, maybe by now people can have computational approaches that would help. So all these fragments were photographed and stabilized and so on, and they made this available on CDs. And so you have many photographs of high-resolution pieces of fragments of these different frescoes. And you see here a couple that had been pieced together. I mean, it's one of the early boxes, and the back of all these were shown as well. And so that was made available, and they asked people to come up with ideas. How are we going to put those? And it really was problematic because, so you can say it's a big jigsaw puzzle, but it's, first of all, a really huge jigsaw puzzle. Second, you have very small fragments, and you didn't have all of the frescoes. Now, fortunately, there were some very good black and white photographs of the frescoes that had been made prior to the war, and so they could change them and put them, I mean, they decided they would make printouts, real size, of these frescoes, correcting for parallax. But so you have the box, if you want, if you think of it as a jigsaw puzzle. But you only had about, you had fewer than 10% of the pieces. And, I mean, it just seemed completely hopeless. So, so I'm going to sketch to you the approach that Massimo Fornazier proposed, and which worked, and we'll then see what the results were. So, if you have a digital image is something in which you tell on your screen at each pixel, at each little point, what portion of red, green, and blue you have to use. So you have, if we don't think of color, if we just think of luminosity, then it's just a whole lot of numbers that tell you how dark or light it should be. Typically you use 8 bits, which what that means is that you go from 0, absolute black, to 255, absolute white. And so in between, we have 254, namely 2 levels, white and black are gone. From the 256, we have 254 levels of gray. So I like to say that other people may have 50 shades of gray, but we have so you might think that it's easy to compare such images. You just look at the numbers, and if they're the same, well, okay, it's the same image. But it's not as easy as all that, because if, oops, it's not as easy as all that. See, if your images are slightly shifted, then the numbers will look completely different. So not only do we have to think of shifts, but we also have to think of rotation, because we don't know where these fragments were. So they may be in any orientation. So how are you going to try out all these orientations, locations? Also impossible. So here are, I mean, I don't know whether you can see the numbers, but these are 2 things where actually at the center, exactly the same place, but that's rotate it one with respect to the other, and you wouldn't recognize that these are the same arrays, because the numbers are completely different. Now, Massimo realized that you can, something that all mathematicians know, but he realized that one could apply this here. Images, it turns out, can be decomposed into elementary building blocks that are called circular harmonics. And they have a very particular role with respect to rotations. So these are these building blocks, and you might think, how can I decompose into that? But let me give you an example. So here I'm showing you, as we go along, a decomposition of that image at the bottom right, using more and more these blocks. One block and two blocks and so on. And you see how gradually you build up an image that looks quite complex from these little building blocks that I have here. So if you have an image and I have these building blocks, then I can indeed write my image as a sum of these. Now, how are images sums? We've decomposed them as numbers, remember? Every pixel is a number. And I can add numbers, and I can multiply them with coefficients. So once I have the digital representation, I can very easily compute all this. And in fact, decomposing, finding these numbers A1, A2, and so on is easy. Now, why is this a useful thing? Well, if you rotate your image, which would completely change all those numbers, then it turns out that if you decompose it again in these building blocks, you can very easily compute the new numbers. The new numbers are the old numbers times some coefficient that you know ahead of time. It just depends on the angle. So if you have one decomposition, then you can easily, immediately compute what all the others would be. And so you can compare with what you find. And so that's what Massimo proposed. He proposed that for every segment, every fragment, they would take a circular area if there was something on the fragment. If it was uniformly yellow, well, so be it. You could not find where that yellow would fit. But if there was something on that fragment, half a toe or something, then you could make a circle, take a decomposition to circular harmonics, then try out that number and put it everywhere in also the different orientations, because you could compute it that easily. And so that could be done. And in 2001, so this is 15 years ago, computers were then not yet as powerful as they are now. Your cell phone can do more than what most computers could do then. But still, computers were powerful enough. A lab was done in the center of Padua, where people could come and volunteer. And so what would happen is that they would extract fragments from a catalog. They would ask this computation. The computation would then spit out 3 of the top candidates where they thought it would fit, and the operator would decide which would fit best, because not always was the top one. It was always among the top 3. In most cases it was the top one, but sometimes there was a confusion possible, which by a human operator would be easily seen. This was long before machine learning was as powerful as it is now. Anyway, but it turned out that the art conservators were actually very happy that people still played a role as well. So this is the result. Here is one of these frescoes with all the fragments that they had, that had some feature on it, which was about 90% of the fragments, were placed. And so they had these pictures in real size, and as soon as the placement was decided, the conservator would go and say, yes, that is its place. It would fit. They would all fit. It was incredible. Here's another one. And you might think, what use is it? Well, imagine this scene. If you have these fragments on this scene, then you really know what the whole thing will look like. Because look, you have the color of the lens, the color of the pavement, the color of the man's toes, you have the color of the leather protection of his legs, you have the back of his shield. Or in this scene, again. And in fact, art conservators are very used to that, to having partial information and then kind of spreading it slowly away from that. And they can fill in. And here as well. And let me show you. I mean, if I have this and this information, then it's not too difficult to see how you can make it into this. So the church, I mean, this is a picture that was taken when the church was being restored. And here is that same, in another scene actually. So the Conservators decided for, if you go to Padua, you can now see this, to show in some places just the black and white with a placement of the color fragments. In other places they filled it in, but they painted in pastel the thing that they painted in, and they left it. And, but you can also, I mean, what I was saying is what the art conservators do is take the information and propagate it and so on. You can do that with equations. And that's something else that Massimo did. He actually designed an algorithm to take from those fragments and to do that mathematical propagation numerically. And so the same scene you can also fill out, and this is what it would have been. I mean, and that you can virtually then also look at. So this is a beautiful way in which mathematics helped get this impression, this beautiful impression of these fantastic frescoes back. So that was the first application I wanted to talk about. Second one is work by Rick Johnson. He is an electrical engineer in Cornell, who actually is the person who got me into seeing that there were very many interesting questions in coming from art conservators that would be really interesting research questions for people interested in image analysis and image processing, which is one of my research interests. Okay, so he worked on automatic thread counting. So let me tell you a little bit about it. So this is a painting by Van Gogh, and if you look at the X-ray of that painting, and I'm showing you a detail of a corner, then you see very, very clearly here canvas. And here you see a small piece of that canvas, and also its negative, on which is even more obvious that you're looking at a weave. So how come that you see that weave? I mean, on an X-ray, I mean, don't X-ray travel straight through a cloth? I mean, how can you see it? Well, of course, you don't really see the canvas. What you see is the primer. So in order to prepare woven fabric for painting, it's primed with a layer that in the time of Van Gogh, and certainly until the middle of the 20th century, contained a lot of lead white. Lead is something that's very absorbent for X-rays. And when you have canvas and you put this layer on, you of course put a little bit more in the valleys between the threads than on top of the threads. So you have these variations in thickness of that layer that contains lead, and that is what you see on the X-rays. So you see this negative, this impression on the lead white on the canvas. Why would one want to count these things? Well, it's when conservators or art historians write what they call a catalogue raisonné, which is a catalogue in which you put everything that's known about a piece of art. I mean, everything that's known that studies have shown and so on. One of the things they do is they characterize the canvas by saying it's a weave of so many threads per inch horizontally and vertically. And the way they used to do that is by looking, this microphone doesn't like it. By looking at the, is this okay? Okay, by looking at the canvas under X-ray, under a microscope, and with something next to it, and start counting. And they would do that in a number of places, and it's mind-boggling, of course. I mean, the eyes glaze over after a while. So you do it in a number of places. But even that research turned out to be useful to show that some canvases were similar to other canvases and so on. So anyway, so when Rick Johnson and I and others heard that that's something they were interested in, they said, well, we could do something like that automatically. Because we have very good tools to look at little pieces of data and see that things repeat periodically. We use a Fourier transform to look at that. So what Rick Johnson then developed was a project in which undergraduates would develop software in which they did this counting. And what happens is, whether you look in this direction or that direction, everything repeats periodically when you look at this canvas. But in some directions, it is more dense than in others. And that's because you're just perpendicular to the threads. I mean, if you're obliquely, it's more spaced out. And if you're... So you can find the directions in which the threads really are, and then you can find how frequent they are. So that's... And then he came up with the idea of displaying that information, since he could do it everywhere. He would display with colors, with false color, this numerical information. You would have an average, and then sometimes you were a little bit above, a bit below. And that varied on where you were. And when he did that, he showed, he did that both for the density on horizontal and vertical, and also for deviation to angle. Because look at this painting here. You see that the horizontal threads are not that horizontal. They deviate. I mean, there's once the thing is primed, you cannot really twist the threads anymore. And if the threads were slightly twisted when they were primed, well, it's frozen like that forever. And so they are like that in the canvas. And so that information gives now rise to 4 different ways of looking. Horizontal and vertical density, and horizontal and vertical deviation with respect to the natural angle. And you start seeing then a fingerprint of the canvas. There are 2 different canvases by Van Gogh that were known to be canvases that he painted on very close together. And it's obvious here that they come from the same bolt of fabric. I mean, like many artists, he would buy the fabric in bulk and then put it on frames, on stretchers individually, because that made it much cheaper. And he would buy primed canvas because that was but that got into pieces. So here are now 6 paintings by Van Gogh that we know were on the bolt. The pieces of canvas were on the bolt like this because this is what one fingerprint gives of these, and this is what another gives. And you see, that makes you place them. So this was no longer a mind-boggling thing and getting many more data, but you could use it for purposes for people who hadn't thought of using it before. And this has now been used, this is the standard way in which this is, which museums these days look at the canvas density of paintings on canvas. And it has turned out to be crucial in reallocating, in reassessing a painting that they thought might not be by Velázquez, and realizing it was, after all, Velázquez. Maybe not as good a one as what he was on his best days, but it was really by him and not by copies. Okay, so as I told you, Rick Johnson got me into seeing that they were interesting things. And let me tell you a little bit about a project in which I was involved. The very first projects were about trying to distinguish style, trying to distinguish originals from copies. And you can still find a snippet on the internet that was filmed by a Nova television program about that work. But a later project, the fun thing with this area of research is that whenever I give a talk to art historians or art conservators, they say, oh my, if you can do that, maybe you can help me with this. And often a very interesting, different, new project comes out of the woodwork. So this was about 8 years ago, 9 years ago. If you went on Google and looked for Van Gogh portrait woman, this is the image you would find. This was a big splash when it was first done. It was known, this was a study by 2 material scientists, one of whom also has a degree in art history, of this painting by Van Gogh, A Patch of Grass, which is a study that he realized in his Paris period. When this painting is turned up on its side and x-rayed, you see that there's something else underneath. In fact, Van Gogh had many paintings where something else was underneath the painting on top. Because canvas was not cheap, he was poor, and so when he made a study and he felt he learned from it what he wanted to learn, he would put a new layer of primer and use the canvas again. About 30% of his canvases have something else underneath. But this one was particularly interesting because the portrait, it shows that there's a portrait of a woman underneath, and people were sure that this was a portrait from the period when he was still living with his parents in the Netherlands. And he was then trying very hard to give an impression of light with a very limited canvas with very dark colors. He had only one light color in his canvas, and he was trying to give an impression of different colors and light. And the correspondence between Vincent van Gogh and his brother Theo has been preserved, and he wrote very often. And there's a letter to Theo in which he says, "I'm sending you here from the Netherlands to Paris, where Theo was living, a painting in which I feel I particularly well succeeded in what I'm trying to do." That letter is preserved, but the painting is not. Now, we have this painting of a study in Paris at a time that Van Gogh completely changed his style and probably did no longer value the stuff that he did earlier in the Netherlands, that has such a painting. So it was felt very likely that this was that painting. And so people were interested, could they do more? And so Joris Dick came up with the idea of using X-ray fluorescence on this painting. What you do there is little bit by little bit you analyze, and you get a whole spectrum of fluorescent spectra which give you signatures of what elements were used. And so by looking at the spectral lines that are characteristic for arsine or for molybdenum, you get an idea of the concentration of that element in different places. Arsine is used in vermilion, and you see how the lips of the figures stand out. Molybdenum is a component of Naples yellow, the only light color he was using on his palette. So that's why you give an impression of the luminance. And using that information, Joris Dick and Koen Janssen had kind of colorized the whole thing, and that's the thing that made such a splash. And people got a much better impression of the painting than they had before. But after he heard a talk of me, he said, maybe you guys know more about image analysis, maybe you can help us. And he gave me the data, and indeed, we did some work. First of all, because of a technical hiccup, you have to understand, in order to make to acquire the data, they had to take the painting to a place where they had the X-ray machine. They had only a single shot of doing that, one afternoon that they could do this experiment. And then it went back to the museum, and no way were they going to get permission to take it out again. Already the insurance premium for taking a Van Gogh out of the museum to put it in front of an X-ray source was mind-bogglingly expensive. It was only a study, after all. You wouldn't do this with a famous Van Gogh. But so there had been a hiccup, and you see the thing had been zigzag things, but some pixels were missed. And so you have, as you see here at the bottom, that you clearly have pixels that were missed in one, and so you had discordances. You had to find how to correct for all that. And so they had corrected a little bit about that by hand, but it was clear that this was happening everywhere. How are you going to find out where to correct and so on? So we devised a variational algorithm by means of which we did the correction throughout, and you see the result here on the right. But then there was additional stuff that we could do. Why do we have these black spots? Well, the top was painted with big impasto. And impasto means thick layers of paint, and so the X-ray fluorescence hadn't been able to get through. And so you had no data there. But the thing was a painting. I mean, you had brush strokes. So prior and after, you saw the brush strokes. So you could, again, like Massimo did with the color in the frescoes, you could reconstruct what should have been there. And so we did that. So here on the right, we mark in yellow what we're going to cover. And then you had to use a slightly different algorithm for these marks of the big grass stalks, and then something around the eyes. And this is what we got. So we already have a much better picture of the woman without all these black spots. We also, I mean, and here you actually can see how nice and in painting, how delicately that works. But, so already we're going to do much better than what you have here on the left. We also did a study of colors, because the colors in which the hand-on measurements, pigments, didn't give you enough of the whole color spectrum. But we then took all the paintings, well, a wide selection of paintings that Van Gogh had painted in that period. We realized that even though some had very little contrast, some very, very high contrast, that there were some common denominators in color distribution, which weren't immediately obvious if you had looked at contrast. If you removed the contrast and you only looked at chromats, and based on that we could then extrapolate, and so we went from that to this. So really got a much better sense of what it looked like. Anyway, so when I moved to North Carolina, I fortuitously met, soon after I came here, I met Bill Brown, who is the head conservator of NCMA, North Carolina Museum of Art, and he'd heard of this work, and he said, would you be interested in working with us? And I was delighted, because it's often very hard to get high-resolution data from museums on their artwork, because they have been told by others that that's their intellectual property. And so they don't, it's difficult to, when I worked with Van Gogh, the Van Gogh Museum, I had to kind of pledge my soul in case it ever leaked. I mean, so fortunately it never has, and so I'm still whole. But NCMA, it's been a pleasure working. So, and that became the start of what I now call an art historical and digital adventure. And this is also the title of an exhibit at NCMA. So, Reunited, I mean, if you Google it, if you do Google Reunited at NCMA, then you will find it. And it became, it's both an art historical and a digital story. So let me tell you that story. The North Carolina Museum of Art has in its collection 3 panels that it got from the collection of Samuel H. Kress, who in his will stipulated that a lot of his art collection be distributed over the museums of the regional cities, the regional art museums of the cities where he had made his fortune with his department stores, which I think was a very classy thing to do. I mean, so it's gone back to those cities. One other painting in his collection went to Portland. But when they arrived, the 3 arrived here at NCMA, the art curator, David Steele, realized that they were similar to 3 panels in the Metropolitan Museum. And in fact, they are clearly by the same hand. There is also a central panel that is in the Institute for Fine Arts in Chicago, the Art Institute in Chicago. And they all belong to an altarpiece that was painted in the 14th century by Francis Cuccio Grisi. Clearly there was a 9th panel. It's not there. It actually, there's no trace of it in the records. It's lost. It probably, this altarpiece was probably intact until near the end of the 19th century, when many churches, for several reasons, no longer appreciating this type of art as much as before, and also in financial need to repair roofs and other things in their churches, took the opportunity that some people had started collecting this art to dismantle it, sell it to collectors, and use the money for much needed repairs. There's no trace of this 9th panel, and clearly already some of the panels were sold to different collectors, and that's how they ended up in different museums. But this was an opportunity, And I had worked earlier with Charlotte Custos, and I introduced them to the museum, and they liked her very much. She is a fantastic artist, but also trained as an art conservator and art historian. And she specializes in, except her own art, in art reconstruction. What is that? That is trying to paint, making copies of art, but using materials and techniques that are completely the original materials and techniques. So here are a few examples. I'll name just a couple, but she does this in many different styles, as you see. Here is a detail of the altarpiece of Ghent, which is a very, very famous painting in art history. It's 14th century as well, by Van Eyck. It had tremendous influence in its own time. And I mean, people traveled from Italy all the way to Flanders in order to see it, artists, and to study it. And I mean, that influence has been mapped. In any case, when this is a big conservation campaign is underway right now, and as part of that, the paintings were all photographed and studied very carefully. They also asked her to prepare copies of a detail and prepare actually 3 copies, which she stopped at different stages, so that people now, when they visit it, can see intermediate stages of a painting of this type. I have another one. On the top right is actually a copy of watercolors by Turner, but because for Turner they actually had a stock of his original paper and they had his original materials. They contracted her to actually paint with his real paints and on his real paper some copies. So they are carefully marked, so they can never become confused with the real thing. Here is one that she made for the museum in Amsterdam, in Rotterdam, which is similar to that. So she I gesticulate too much. If I were a robot, the screws would be falling. Anyway, so here is, so she stopped about a centimeter short, a quarter-inch short every time. So you see at the very left the raw wood, and then wood with some of the layers of glue. There are many layers that get applied. And then you have the layers of backing, I guess so. And then you have the drawing and fixing the drawing and so on. And you see it only near the very end is when she starts painting. By then several months have gone by of preparing. So, and the impression it wasn't working, so, okay. So, back to Gissy. Here we don't have an original. How are you going to make, yes, you may master all the techniques, and in this case actually there was a book written in the 14th century by Cennino Cennini about how to do this. So you even have a manual on how to do it, and Charlotte followed this very carefully in preparing this panel. But you don't have an original to copy. Well, however, you have a central crucifixion here, but you have these 8 other scenes. And they are scenes from the life of John the Evangelist. And those scenes very closely followed a book that's called The Golden Legend, which was a medieval bestseller. I mean, and I'm not using this word lightly. Most books from medieval ages are kind of rare. I mean, not very many have survived all this time. Of this we have hundreds. So, I mean, everybody who could write must have wanted a copy, or everybody who would commission one must have wanted a copy. So, Golden Legend, so we know the story, and it's very likely which scene is the last scene that we don't have. There are also other altarpieces that know this. So they could determine what was the scene. And so a compositional drawing was made and corrected. And so they tried to also take something that was very much in the structure, using the same stylistic elements of the rest. So clearly, if this panel is ever found, it's not going to look like this. It's going to look different. But this panel, in the 14th century, would not have surprised. That's what they wanted to get. So at the museum, you can see a video with documents her making this, all these different stages of applying glue to the wood, applying gesso, preparing a special layer of what's called gesso sottile, which is a very fine gypsum. It has to be massaged in and then scraped. I mean, like all work. I mean, I remember learning to paint when I was a teenager and being dismayed at how much layers you had to put up and then completely almost sand off before you could put a new layer on in order to get a good result. But so she's doing that. They did that in the 14th century already. So scraping it off. Here, applying the background layer that is put underneath the gilding so that you can polish the gilding. This is a layer of clay particles. Clay particles are long and tile-like, and the result is that they can slide on each other. That's why you can throw a pot when you work with clay. But it also means that when you put a layer of such clay particles underneath gold, that you can still manipulate them slightly, very little, but enough that it makes it possible to polish it and get a mirror-like surface, which these paintings were in when they were new. So here she's applying the gold. She's applying the gold, and is this still working? No, it's red. Sorry. Shall I talk louder?
Yes.
Okay. So, I have another one. So she's applying the gold, and this gold, I mean, it's incredible. It's so thin because gold is expensive. I mean, if I even glance at it, it starts to crumble. I mean, I'm serious. I went to a workshop that she organized, and I sneezed, and I had nothing. And so here, you see, she's polishing that gold. Here she's punching it. In order, so this gold would have been mirror-like when it was new, and then it would have had this relief punched in. This would have the effect, here you see the punch marks, so she had studied the old panels, had punch marks made by another art conservator, which she then used, and here you see her at work. And the result of these punch marks is that you have a beautiful light impression. So we're back to this microphone. So now I can use both my hands. You see. It's very important. So you see here the effect of with the reflections on these punch marks. You have this lighting up of the halos around the heads of the saints. Ironically, with aging, the gold becomes a little duller. I mean, and things flake off and so on. If you start polishing that, it will all flake off, so you can't do that anymore. And then there's dirt that gets in all these slight crevices made with the punch marks, and so it becomes dark instead of light. So, but it's the new panel was is absolutely glorious. You can see it at Reunited at NCMA, and it's when it was finished. I mean, a documentary was made on how she made it and so on, and you can also see the materials at the museum and the punches, the actual punches she used. And then they realized they had a problem. It's beautiful. It's wonderful. And they said, if we put it next to the others, people will only look at this new, shiny, beautiful one. And the other ones are the 14th century originals. So what have we done? And I said, well, you know, mathematics can help. With image analysis and image processing, we could first study the old panels. We can see the correspondence between old and new colors. We have the new ones now and the old ones. And we could use that detailed study to age the new one. And so that's what we did. And the aged one, virtually aged one, was then printed out and put in the frame next to the others. And it looks so good that when the other panels, which came from the different museums for this reunion, this exhibit, saw them all together, they scolded the local curator, they said, how could you do this? Make a fake. And he said, but it's not made, it's a printout, it's on paper. I mean, nobody is going to be fooled if they ever look at it, but it looks so good. And to do that virtual aging, we had to do the color correspondence, we had to introduce cracks, and we also had to age the gold leaf work. But with having done that, we could do the reverse. We could, in the old ones, virtually high-resolution images, we could detect the cracks and inpaint them. We could do the correspondence in the other direction. And then we could try to rejuvenate the gold leaf work. And we did that. So, studying the crack allure is very, very dense. And you might think it's easy to detect. I mean, in Photoshop, I just put my mouse and take this pixel, I take that blue, that brown, and yes, I heard somebody laugh. It is laughable because it doesn't work. Because look at it. I mean, the crack in that green dress has a different color from the crack in the orange background. I mean, partly that is because we're looking at a photograph and the neighboring colors have influenced. I mean, because we're looking at things only a few pixels wide. But partly also because when a crack forms in one medium, the surrounding medium has now access, chemical access to what's happening there. And since that it's a different medium than over there, the cracks may change. They have different colors. There's not only that, so that you have different colors in different places, but also the browns are not the same within the crack. And then even if you find all those browns, there are tons of pixels in the painting that have generally that brown as a color. So you can't say, take all these browns away and make them orange. I mean, you would get a very interesting picture, not what you want. So automatically detecting them is not easy. Now, why was I confident we could do that? Because we had experience doing that. We had, in fact, worked on, remember the altarpiece of Ghent? This is what it looks like. Open, it's glorious. When you close it, it's a polyptych. This is what it looks like. You have this scene of the Annunciation in the middle on the right. Behind the main figure, the Virgin Mary, you have a book on the stand. And people have been wondering about that book because they were saying, look, if Van Eyck, who was a perfectionist, really painted the text here, then probably this text has some meaning. And many said, look, I mean, he probably didn't paint the text. They couldn't read it. They couldn't read it because it's full of cracks and so on. And also these letters. I mean, these are letters like in medieval books. I don't know whether you've ever looked at medieval books in museums. I can't read them. I mean, it's all horizontal and vertical lines. And it doesn't make any sense to me. But of course, specialists can. But specialists could not read this. Because those cracks, again, had the same browns, many of them in the same direction as the letters. And so many people said, look, he may have been a perfectionist, but on an area that's about 3 inches and on 1.5 inch that's on this thing of the closed, he didn't really paint the text. He did just a proxy, imitation. I said, but you know, if that's a question you're really interested in, it's an interesting question for us to try to process that. And we worked at it very, very hard because it was much harder than I thought. It became part of the thesis of an electrical engineer in Brussels. But we did find a way of finding all those cracks automatically and in painting them. In painting them using only the fact that we knew there were brush strokes and so propagating. Not using by any means that there were probably letters or not. And when I saw the end result, I said, well, that was a hard job, well done. And it's been completely useless because we can still not read anything. And indeed, I can't. But experts could. Experts said, oh my, look at that. Look, this is a piece of an A, not of a W, and so on. And so they identified, without any ambiguity, 12 groups of words, which completely, convincingly characterized this as a page of a text on the Annunciation by Thomas Aquinas that actually had been copied a few decades earlier in Bruges. And so the art historians were absolutely delighted. And now they actually want to see, since several copies were made, where they can trace which copy actually was used. That's a different matter. But so, yes, we can detect cracks. So we could do that on the GISI. here you see cracks, and so we could inpaint those. And here you see a result of inpainting cracks. And here you see several intermediate stages. Gradually, by these mathematical algorithms, once you have found the cracks, how you can fill them in. Here is another crack filled in, and it's not perfect. I mean, we weren't out to try to make chromos. I mean, otherwise we could easily have hired a cartoonist and try to make copies of it. What we were trying to do was really, with scholarly methods, give the best possible impression based on what we have now of what it must have looked like then. So that became an interesting exercise also for the digital people. So here is one of the metropolitan panels, and this is what it becomes when you remove the cracks. In the gold, we didn't remove the cracks everywhere because the gold had several treatments, but let me toggle back and forth a little bit. No, okay, so toggle back and forth. If I look only at if you remove the gold, then now we see it already makes a big difference to remove the cracks. And we haven't done anything to the colors yet. So the colors, well, we had the 8th panel old, the 9th panel new. And actually in the same light conditions, the gold doesn't come out so well, but you see the colors much more vividly on the right. So these two panels here were photographed under the same light conditions. So it shows you, if I take the gold away, how the colors have really changed. Look at the red mantle of the guy with the turban. Look at the blue and yellow silk robe of the person kneeling and who was standing. Look at John the Evangelist. I mean, his deep blue dress is painted in something called azurite, which is made of lapis lazuli ground. And it's made of azurite ground. It's called ultramarine. And so when you want a deep blue, you don't grind it as finely because then it becomes much flatter. But that means the paint is more grainy. And that means that it accumulates more dirt over the 6th century since it was painted. And so many of these deep blue robes now look almost black. I mean, because they've accumulated so much dirt. So because the previous one had been used as inspiration for the new one, there actually are areas that are very close in drapery and everything. So you can look at detailed areas of color comparison. In any case, you can, using that, you could age, you could rejuvenate the old one, which is what I've done here. I mean, I've taken the 8th panel and rejuvenated its colors. Or I can age the new one, which I've done here. On the right is the new one, on the left, the remapped one. We actually were very careful in doing all that because here you see the vermilion itself hasn't changed too much, but the highlights on the folds, which were painted in lighter color, have a different chemical constitution, and that has turned grayish over age. And so you see the highlights are still there on the left. They haven't faded. Some other things have faded. But those highlights are still there, they just are gray. So we changed all that too. Here, actually, I hadn't done it yet, and I made them gray. I also put in all the cracks. How did we get the cracks? Well, we looked at the cracks of other paintings. Since we could locate them, we could look at the network, and then we could take pieces of it, and we copied pieces of it in the right colors. We also used them for the gold. I mean, so if you have the new panel here in Chinese shadows, I added the gold, I add the gold halo, I add the painted cracks, and this is what you will see when you go to the museum in the 9th position. And it looks perfectly in accordance with everything else. To rejuvenate them, we had not only removing cracks, which we know how to do, remapping the colors, which we have studied and can do, we also had to do something about the gold. Because the gold, we didn't only have to remove the crack, we had to give you this gilded, this shiny impression. And we had to get the punch marks. So the punch marks, we identified what the punch marks were. Charlotte had done that in order to get them manufactured. And you see here the traces of punch marks in details on the different panels. In some of them they were very, very worn, and how they were on the metal shapes that she had manufactured, she asked to be manufactured. Here's a panel of the Metropolitan Museum, and we did this originally. I thought we would do this by machine learning, and I think we still can do it, and we're still talking about it. But for these panels, there were only time was getting short, and we decided to just, once we identified the shapes, to inspect it by hand. And so you see here, I've marked all the marks on top of this panel. And this is what the panel comes when you have these punch marks in the right position and nice gilding on the back. And let me see whether this works here. If you go to the website, so we made a very nice website of this whole exhibition, and let me go to the top, of the do group that worked on it, the Image Processing for Art Investigation, IPAI group, and we use the same fonts as for NCMA in order to be clear that we work with them. Then this gives you this description of the project with some of the images I've shown you. Here you can actually see the crack removal. And you see new and old with cracks, new, no cracks. And for all the panels, and let me show you the one that we were just looking at, here, it gives you a slider between the rejuvenated version and the old version. And so at the museum you see this in the slideshow, but I highly recommend you will see it, and I hope it will appeal to both people who like medieval art and this art history, and to people who like who are nerds and like this. Thank you very much.
We have time for some questions. If there are any questions from the audience, just raise your hand.
So I didn't understand if the panels were actually, if the old panels were actually restored, or if they were just done by image processing, and we'll see the image.
It's only done by image processing. And so what happens is that at the museum you can see in a nice frame that was fabricated for it, and I think I have a picture of that here somewhere. Well, maybe lower. Oops. You see a nice frame that was made specially for it. We have, no, I don't know. You have, here at the top you see that frame. You have all the panels displayed in their original shape. Now they were restored in the last 10 years sometime, but before this work, together with this printout of the aged version of the new panel. You also have on a separate wall the new panel and the materials used to make it, and a very nice documentary on how it was made. And then you have on a separate wall you have a large screen, a large television screen that shows you an animation of the old and the new, and it even shows you how some of the light plays on it. And I think I have one image of that here, although once it's still you don't see it so much. I mean, here you see gold is something. How do you see that something is golden? It's because as things move, as you move your hand, as a person who's wearing jewelry, or the reflections change. That's how you see metallic things. I mean, otherwise they're just some bright spot. It doesn't. But so we decided that we would have that modeled by computer graphics. So once we'd done the thing with painted surfaces, it was modeled then in 3D on a thin board with the painted surfaces and with a golden surface. And then the punctures, all these punch marks were also modeled, and so those reflect the light differently as things. And that you see in animation there. And I don't have an animation of that here. What I did for a printed version, actually you can from this website also print out a version. Let me find you. So we have a nice booklet that of about 8 pages that describes from different points of view. Everybody wrote an essay, and you can download the booklet. It's not offered for sale at the museum because when I started to put together the booklet, I said, "Oh, there's no way you can put together a booklet in 2 months' time." I said, "Yes, I can." And I mean, my husband learned a long time ago not to tell me, "You can't." And so I did, and then they said, "Oh, it's beautiful, but you know, we will not be able to offer it for sale as a catalog because we had not negotiated with the other museums that we could offer something that printed their work. We can," I said, "but you told me I could use it in publications." "Yes," they said, "in publications, in scholarly work, it's okay, but not in a catalog we offer for sale. We would have to negotiate that a year back." And I said, "So can people download this if we offer it for free and we don't print it for them?" I said, "Yes." So that's why you can download it. So you can download this here. And so for the print version, we prepare these images that I showed here with a slider, but they are a real cheat. I mean, well, cheat in a sense, they use all the information, but I took from the Wikimedia Commons a photograph of a gold sheet. And I had the punch marks, and in order to give you an idea of the punch marks, I took from a photograph of the punch marks of the new model. I took different colors of the reflections, and I printed them with slightly shifted, and that gives you a good impression. So in that sense, it's a cheat, but a print sheet. I mean, if I did it in large things, then you would see it immediately. But for the large screen at the museum, we show it with the 3D graphics.
Are there any other questions?
This was lovely, and I love the art, but of course the mathematics behind it is fascinating. Have you published the math that you used to implement all of this?
Some of it. So the crack removal was published in a paper that appeared in and I think it's certainly written in the bibliography in that booklet that you can download. We also actually, something I haven't talked about, but as a side vein on this, we looked at X-rays of these paintings on panel. And we then discovered that they look almost like if they were behind prison bars. So maybe I can go to that side as well. So if you look at X-rays of paintings on wood panel, then they look like there is stuff there. Do I have a gallery here somewhere? Yes, gallery. They look like things here on the left, like you have a lattice over them. That's because these paintings at some point were originally on boards about an inch thick. These boards were thinned by conservators in the 19th and early 20th century, mostly because they wanted to keep things flat instead of warped. And then they put on the back a lattice that is called a cradle to give it structure. But then, of course, when people use X-rays because they want to look at the brushwork, all you see is this lattice. And it's very hard to think away. And so when I said, let's show us the X-rays because those are good to find the cracks, they showed us this. I said, what's that nonsense? They said, it's great. I said, aren't you annoyed by it? They said, oh yes. And Now, if it had only been for the Gizzi panels, we wouldn't have done it. But then I discovered that all paintings have this. I actually went to visit the Prado Museum, and I asked the conservator, said in NCMA, they told us they're very annoyed by this. Do you have this too? And she, Spanish Mediterranean, says, do I have this too? Look! And all her x-rays of panels have these. And I had a student who worked on this for part of her thesis, and it was mathematically very challenging, because not only do you have to find the location of these and remove it, the gray level, of course, is not constant, but, I mean, once we started working on it, the conservators became greedy, and they said, you know, there is wood grain in those cradle pieces, which you can kind of clearly see here, and we'd love to get rid of that wood grain, but we want to keep the wood grain of the panel. I said, are you serious? And I said, well, can you do it? And so my student said that she could try. And so in fact, she did use machine learning to, once she had removed the, so this is just the first effect. The wood grain is still here. But you can remove the wood grain as well. It's very lengthy. I mean, you have to learn from the places that have panel wood grain and from the ones that have panel and cradle wood grain, what the differences between the two, so that you can remove the cradle where it is present. But she brought that to a good end, and we then actually developed a software. I mean, we first ported it to C++, which I had I knew a student who could do that. But then we had to write the interface for Photoshop, because that's what conservators use. I mean, anything in one of our codes is not going to just as well be in Martian. I mean, so we had to name it. They said the first thing they needed in order to organize their files was a name. I said, well, virtual cradle removal tool. I mean, and Noël Lecaux, the conservator from the museum, said, maybe it doesn't have to mean anything. Maybe it just should be a name that people remember, or something silly like platypus. So it became platypus. And so platypus is sitting in her cradle and climbing out. And at the very end of the booklet, so maybe we can, I don't know how fast the download will work here. We see. At the very end of the download, so let's go to the very bottom here. I don't know, I might not be able to show it. So you can see that platypus will have climbed out of her cradle. So, well, anyway. So at the very end, we show platypus having climbed out of her cradle. And in fact, we made this development of the software, which has been online for about a year, has been downloaded by over 100 users, of which over 160 museums, which we make freely available. We not only make it freely available, we give it's open source, and we give the full package, the papers, the mathematical papers, the MATLAB code, the C++ code, and so on. And the idea is that if people want to do something with it that we had not foreseen, our conservators can go to local mathematicians, applied mathematicians or engineers, and they will be able to use that MATLAB and C++ code and do other things with it. But since it's open source, I mean, it can be uploaded. And so I hope this way to spread this very interesting applied application field to other groups. And so this was all done with a grant from the Press Foundation, because we were working on press paintings. But platypus could learn a whole lot of other things if we find the funding for it. And we're thinking of writing proposals.
Okay, let's, if there are any more questions, Dr. Daubechies will be here down in the front. But let's just take a second to thank her again for the wonderful talk.